Take it away, Pontus.
Yes, so hello, I'm Pontus, and welcome to my talk called Beyond the Option Type. Okay, so like I said, I'm Pontus Nagy, aka Pixelero on the internet. During the day, I'm a front-end consultant. I do mostly React and TypeScript. And during the night, I like tinkering with typed functional programming. I don't have any OCaml or Reason in production. We'll have someone else talk about that later. And I'm a bike shredder deluxe. I like my dot files and yeah, those things. And I'm also a co-organizer of the ReasonSTHLM meetup. So I'm just gonna talk a bit how I got into functional programming. So I basically started with React like 3 years ago and got into Redux. And Redux started talking about these things like pure functions and immutability. And for me, those things, those concepts like really worked for me. So I started looking up those concepts and discovered like these are concepts that coming from mostly functional programming. So I started dabbling into functional programming. I started up with Haskell. So going from JavaScript to Haskell was quite a fun experience, quite the opposite. And when Reason was announced, I jumped onto that train a bit. And I've been like pendling in between Reason and Haskell since then. And also a little bit interesting in category theory. I think it's most people like Haskell are also a bit interested in category theory, even though it's a like really abstract concept. I'm not pretending to understand everything about it, but it's fun to dabble in. And now I do mostly OCaml or Reason. I try to like mix them up because I believe it's kind of the same thing. I'm a front-end developer, so for me it's fun to actually do something that runs on my machine that's not like Electron or something in Chrome. So I've been dabbling a bit with EC and Reason Native or OCaml Native. And this talk basically started off with me building a small like command line tool to manage my dot files or symlinks, because I have a GitHub repository that's on my machine, and then I symlink all these configuration files to different parts of my machine, and that's my configuration. So I wanted to build something small for myself. And I wanted to handle errors as well, because I know a lot of programmers don't handle errors really good. And also, I tend to run into a lot of errors during my job, basically, when I'm a front-end developer. Like we have a lot of things that can go wrong. We're fetching data, we're parsing data, we're doing things. Yeah. So I think error handling is really important thing in programming. And I think it's sometimes overlooked. And I'll hope this talk can like broaden your understanding how you can handle errors in Reason. So what are we going to talk about? We're going to talk about some concepts we can use to handle errors in Reason. We're going to talk about variants. And those variants are the option type. And we're also going to talk about this thing beyond the option type, my clickbaity title, the result type. And we're also gonna, okay, yeah, sorry about that. I'm just gonna put the chat here so I can see if anyone has a question, which I think is good to answer during the talk. So you can just write in the chat, and if I think it's a question I can answer during the talk, I'll just respond. We're also going to talk about how we can compose types, because that's an interesting thing about types. When we have these like algebraic data types, that we can compose them, and I think we can build some really cool concepts with that. And we might also, depending on the time, talk about polymorphic variants. That's a thing I've used in my command line tool a bit. We'll see about that later if we have time. And yeah. Okay, so we're going to start off with this thing. So this is a type signature for a function defined in the list module. You can define these like type signatures in the REI files, like the Reason interface files, and then basically set the types for your functions. So this is the head function. What the head function basically does, it takes the first element of a list. But the type signature doesn't really convey that. The thing with this function is that the function can also raise an exception, and that is if the list is empty. But the type signature doesn't convey that information. The user can't really see that the function might raise an exception. And I think type signatures can be used in a powerful way to convey what we want to do, what we can do, and what can crash during our program. We can respond to those problems. Here we basically need to read the documentation about the list function to see that the list function can raise an exception. So we want to use type signatures to convey meaning. That's basically my thing about this talk. So I follow a lot of like functional programming people on Twitter, and this is not a direct quote, but this is probably something some Haskell person has said, like friends don't let friends use head. And this is probably a bit more serious in Haskell because Haskell is a pure language, whereas in Reason we have mutation and exceptions in Reason are actually values as well. We can operate on them. But we can't see the exceptions in the type signature. So we're going to jump into that a bit. So we have this type signature, and we can change this with a so-called variant, which is type. And it will do something like this. We can define our head safe function. It takes a list and returns an option of A. So what this basically conveys is that if there is, the first element is present, we retrieve it. If it isn't, we return nothing. And we look something like this. And I argue this is like, for me at least, this is like the hello world of algebraic data types. It's pretty easy to implement, it's pretty easy to understand, and I think it conveys meaning because the head function can only fail in one way, at least I think so, and that is if the first element isn't present. So by getting the none value from the function, we know, there's no element in the head. And if we get the value, everything's fine. But I think using the option type here is only conveys value because we're lucky, basically. Because the fallout of this function is basically like binary. We only have two things that can occur. And that is empty or not. So it works here, but whatever we have a function that can fail in other ways, they can fail in multiple ways. We're going to talk about that really soon. But first I'm going to show what the variant actually is. So this option type is a variant. I said it later. I said it previously. And here are some other examples of variants. So a Boolean is a variant. We can define our own variant, like the color type here. We can also variants can also have payloads in them, like another type. So we can have an option type of alpha, this is called. So this A signals that this is another type at runtime, or compile time as well. But the cool thing about the list function here, that the list operates on everything basically. So the concrete type would only be there at runtime when we put a list into the function. So, like I said before, what happens when we can fail in multiple ways? I don't think the option type conveys this in a really good way. So I'm gonna show another example. If we use this head function and then we do something else with it, we basically call the function and do something else on that. So imagine we want to retrieve the first element of a list, and we want to try to parse that element to number. So we assume the elements of a list is a string. I want to use a string and parse it with the int of string function. And the standard library, or the standard library, I think it's called pervasive, or yeah, I'm not 100% sure. I can look it up later. Actually has like a safe function called int_string _ opt. It basically tells you that this returns an optional. But this code, it basically returns an option of int, and that basically means we can return some, number, or none. But the caller of this function wouldn't be able to see where we actually failed. Sometimes in our programs, we want to sequence things. And if we want to sequence something and something goes wrong, we want to convey what kind of error happened. Where in the sequence did the error occur? And this kind of lacks this. So I would argue we can, instead of use the option type, we can use something like the result type. And this is just another type. We have an alpha and a beta as well. So here the data constructors for this type is OK. That's basically when we succeeded, or error of another type. And this pretty much gives us endless possibilities, I guess, how we can convey our error to our users. So we could do something like this instead. So we have same function, but now we return a result type instead. So the first line there is just the type definition. Normally you can't, I don't think you can write the type definition like this in a normal .re file, but just mash them together to show the concept that this function takes a list of a string and returns a result of an int string. So here we can actually tell our user why the error occurred. So we can say like we could not convert the string to int, or that the list is empty. So it's much easier for the caller of the function to understand what happened when things go wrong. But like I said before, the types, they compose. And the cool thing here is with these like algebraic data types, we can use them together. So I think there's an even better way to convey this without using strings, because strings are kind of, they're not very pleasant to use. We like to use strings like in the outer boundaries of when we like communicate to our user using like normal language. But in the core of our program, we don't want to use strings to like define behavior. So my idea here is to use another variant for this. So we can define our own variant called head int error. It's not the best name, but I think the values represent the errors kind of good. So we have an empty list value or the no parse int value. So then the implementation will look like this. So now instead of returning a result of int or string, we return a result of int and head int errors. And it's much easier for the caller of the function to use this, because the compiler with the exhaustive checking of the switch statements will be really nice to you and say like, you're missing the empty list statement, or you're missing the no parse int statement. And it might do that with strings as well. I'm not sure. There might be someone else that knows that, but I think it's much easier to handle if you're the caller. I think that's pretty much it for the result type. Like, let's see here. So we can compare our different implementations. Like, so the first implementation, just to summarize, the head say if it works and it conveys meaning. But I argue that it conveys meaning by accident. Like it conveys meaning because the sum type, the option type, it matches the outcome of the function. So that's a good example. But if you want to compose that function with another function, so we can fail in multiple ways, I argue it's better to use a result type, since we can't really differentiate the none and the none in the case where we fail to parse a string or the list was empty. And then we can use the strings, but the strings are a bit annoying and not very precise. So then we can define our own variant to convey the error. Yeah, I think that's it for my slides. This went a lot faster than I thought. I usually talk pretty fast. I have some code that I might be able to show. It might be a bit like just YOLO it, or might be fun to show. So that's it for these slides. Do we have any question? And I might jump onto polymorphic variants and how we can use those in our programs to be even more like compose different parts of our program. So thanks for listening to these slides. And just for the bike shutters, the font is a Usoveka term. It's the Usoveka font without ligatures. And the slides were made with MDX Deck and Code Surfer. And the color is generated with a thing called PyWall. It's basically take a screenshot of my desktop and generates colors. Yeah, do we have any questions regarding this? Is there anyone that didn't understand? I think is the question for the viewers. How many here actually like use Reason a lot, or do we have any like newcomers? And I can't actually see I can only see the chat right now. I can't see the webcams. So I'm gonna swap screen and just yeah, I know. You can prove that later in a couple of minutes. So I think yes, might yeah, cool. I think I might. Let's see here. So I'm gonna. Yeah, okay. You never use Reason, and you started out. Does this make sense? The thing with these like slides, I don't really know where to like put the level. Because I've done a lot of talks before about like algebraic data types, like introduction to algebraic data types and how we can use them, etc., etc. Is there anything in here that is unclear? We can go back to the slides and we can show some examples if needed. Or we can jump into the more like CLI tool thing I've been building. Okay, that's perfect. So let's see, I need to share another screen. Let's see. I need to share my, let's see here. Share. Okay, let's see. So here, can everyone see my editor now with the code I just showed? Okay, perfect. So this is just like to run these examples. I'll be using a tool called Easy, which basically like is a sandbox for native Reason. Also, I love the language server protocol we can use for getting type information, etc., etc. This is the same font. You see, this is the same color as the slides. So I basically use the same color and font as the slides here. Is this big enough, or should it be bigger? Is that better? We can use the OCaml or Reason language server to see the types here. And as I talked about the list and the option. But I'm gonna show a new concept called polymorphic variants. But first, I'm gonna introduce you to this little thing I started to build. So, like I said, I wanted to build a. This is the OCaml code. So this actually started out like an OCaml project, and I basically used reformatted to transfer everything to the Reason code. It's really like smooth. Just go between them if you want. So I wanted to build a tool for symlinking files. So I have this Git repository with all my, it's called the dot files, where I have all my configuration. So I have, I'm using Vim, and this is my Vim configuration, and there's a lot of things and blah, blah, blah. But these files can't really be in this, in my home/dot files. So I symlink them to the actual paths on my machine, so the programs can read the configuration. And then when I update my repository, the files on other places on the machine will update as well, because they're symlinked. And then I can just use Git and push this configuration to GitHub. And I wanted to try to build something for myself, just a small CLI tool to manage these dot files. And I haven't really gotten far, but the thing I started with is like, I want some kind of configuration I can read. So I can just define the configuration with links and everything, and then I can run the program, read the configuration, and link it according to the configuration. And so when you're using Easy, which is this package system, using a program called Dune. And Dune has a configuration file, which is an S expression, basically. An S expression is this Lisp kind of thing. It basically has two elements. It has a list and atoms. So a list are the things between the parentheses. So this is a list. And the list thing contains an atom, which would be this. And then we have another list, which contains atoms, and another list, and an atom, two atoms. No, I also only use it on this machine. I have the subsystem for Linux set up on my gaming machine at Debian inside Windows, and it works kind of good. There are some things that differs, and also all the terminals on Windows are trash right now, at least. I'm hoping the new one will be better, but it works. It works kind of nice. Right now, I just have like a little shell script that links everything together. It's very primitive, but it works. I don't know if building a CLI tool in Reason is the most pragmatic approach to solving this problem, but for me, it's more about doing the thing than actually solving the problem. I think it's fun to use a language and learning new things, and yeah, et cetera, et cetera. But I wanted to have something like this, just a little file with the source and the target. So we need to do a couple of things here. We need to read from the file system. So reading from the file system can fail, right? If the file isn't there, then we need to parse this thing into an S expression. And for that, I'm using a library by Jane Street. And I think Jane Street, I think they seem to be using a lot of S expression in production. It seems to be like one of their go-to like data, like thing in the store configuration and show things basically. If you read Real OCaml, I think there's a bunch of chapters about S expressions. So it felt like a thing that felt like a bit OCaml reasoning. So I wanted to try it out. So the concept here is very basic right now. So it's a list with sources and targets. So the idea was to read this file from disk, parse the S expression to get a config file that will look, oh, that's the actual, let's see, a model that will look something like this. So we have a symlink type, basically a source and a target. An fpath is a library that basically handles paths on your machine. So we don't want to have the path represented as a string when we're actually in a program. We can read a thing like a string, then we can parse the string and create this like a path thing that helps us with a bunch of stuff. And the library is called fpath. I can talk about a little bit more about the libraries later. They're all by the same person, and I think they integrate with each other really good. Okay, and our model is basically a record with a symlink property that has a list of these symlinks. And this map's kind of good to the configuration file, right? Like, so this would be a record in Reason, and this would be the S expression on our disk. So the first thing, so this code is gonna look a bit overwhelming, but I think the most interesting thing, or overwhelming for some, if new to this, if you're a professional Reason developer, you'd be like, oh, that's easy. But what I want to show here is the concept of polymorphic variants. So we don't need to look at all the implementation details, but we can look at the types, and we can learn something from looking at the types. Because like I said, this varies, then we have the error. And in this case, the error will be this variant. So we can represent a different kind of errors. So the type is literally nested. So it's a variant within an error. And the way we do this is with something called a polymorphic variant. And a polymorphic variant is like a variant, but it's polymorphic. You basically don't need to define the whole variant. So we don't need to write out type variant equals this or this or this. You can just basically shove this backtick in front of the type, and the type inference in the compiler will evaluate all the polymorphic variants and create a variant for you. So an example would be this. So this is like the deepest part in our program. This is the thing that reads a link. It takes an S expression, the list, with the two elements, and reads the source and the target. This actually does it on a list, so we can just check the type signature here. It's gonna look a bit weird because we're using like easy, and we have this like this S expression library, but the gist here is the input value is a list of this S expression. So that's the thing we parsed from our configuration file, and we would return a result, which is either a list of this symlink model. So you see at the end there, we have the model.symlink, and that's the record type I showed you before. Or if that doesn't succeed, so you see we're in the result type here. The matching parenthesis is, this doesn't work in Tmax. So I have this parenthesis, and then we have the one here. And so this is the so-called polymorphic variant. And this is indicated by the brackets and the little bigger or less than. So this basically tells us that the result type can return either a list or this polymorphic variant called invalid symlink, which is a list of S expressions. And I want to store the value from the invalid symlink to basically tell the user like, okay, here's the list of all the things that were invalid. So we get the S expression value back, but the S expression needs to match our model because, let's see here, I'm going to open this file again. So doing something like this would still be a valid S expression, but in the case of our program, it needs to match this. So we can still parse the S expression and get the X expression as a value in our program. But then what we're doing, actually parsing it again and saying like, okay, so our program, it needs to match this shape. We need to have 2 elements in the list. And the whole thing needs to be a list with lists of 2 elements. So this is the thing we're doing here. We're basically saying, so if there is, so this is the pattern matching. If this thing is a list with an atom, with the S stands for source here, and another atom with the target value, then we create this model. And if not, we say this thing is invalid, and we put it in the invalid array. And like I said, the implementation is not really important here. The important thing is that, so we created this error type here called invalid symlink. And we created it by just typing this thing here. So we don't define the type here. We just, yeah, this is the polymorphic variant. We just shove it in there. And then we go to the function calling this function. So read rules is the function that calls this read link. So read rules, the type of read rules is that we get an S expression and we read that S expression. So here we do our first check. The first thing we need to check is, okay, so the config we read, is the config, the outer thing in the config, is that a list? Because if the S expression looks something like this, then we just have an atom, and we need this to be a list. So we need the outer thing to be a list, and this is basically the thing this read rules is doing. So we're checking if this is a list, then we continue with the list and read the links. And if it is an atom, like I just showed you, then we say like, okay, this is invalid. It needs to be a list at the top. Then we return an error with the invalid config. So here we have another polymorphic variant. But the interesting thing is that this function returns the result as well with a polymorphic variant. But the amazing thing here now is that the read rules function, the inferred type, will use the polymorphic variant. So now we see, so this function, you can either throw an error, or not throw an error, you can return the value invalid symlink, which is the polymorphic variant, or you can return the invalid config, which gives a string, or it can return the result. So we just kind of like, without actually defining the type, the compiler have created this type for us. So this is not something we've actually written anywhere. This selection is kind of weird, but you can get the gist of it. But the compiler will create the type for us. And I think that's the thing that makes them polymorphic. We actually don't need to define the type. The define is very, I don't know the actual naming from it, but it feels very polymorphic to me, I guess. And let's go down here. So we have the read rules. We don't need to talk about like everything here, but basically our program starts with reading a path, and this path will point hopefully to our file, and then we load the config. And this is the part when we're actually reading from the I don't remember what it stands for right now, but we can look at it later. And this is just some boilerplate to actually create this. So the thing we get here is this F path, and we normalize it, and then we append the config file name. So this will be the real path to the file we're reading. So the name of the file is hard-coded right now. So the file you want to read needs to be named bopped right now. And then we'll read that file. And so this function, it returns a result with a string, which is the content of the list, or it returns a polymorphic variant called RResult. And RResult is this wrapper library, also from the same person who did this boss and the like pretty much all the libraries I'm using except for the S-expression one. So this is another polymorphic variant called rresult.r.message. And this error is like really verbose. I'd say, like it's mostly string, but this is something like when we're reading from the file system, I think the implementation actually uses tools on our computer to read from the file system, and those tools usually like thrown out like a CLI tool, usually reports back to you with a string and an error code. But here we're just seeing the string. And then when we loaded this config, so this is the actual like program. When we loaded this, we call the load config. We use this. We're not gonna go into this. I was gonna go into it, but the talk will be way too long. I think I'll do that on the next meetup. The people who know what it is, and those who don't, I can't really explain it to you like really good right now. That will be something for the next talk. But then we're calling the read config. And the read config also returns this rresult.r.message. So now this is another polymorphic variant. So see, we haven't defined these types. We're using this utility function from R, which is the part from the result library I'm using. Yeah, exactly. It's called bind. It's like this is yeah, it's called bind. And this is something when we want to compose algebraic data types and sequence them. So we have something that returns an option. We want to put an option into the next function, and we're using this. So it's kind of like this operator, the pipe operator, but we're doing it with like our option type or our result type. So this is basically a way to sequence a function that accepts and returns result types or option types or other algebraic data types. I'm not sure if I'm allowed to say the M word, but yes, it's a monad. So now we have this parse function, which is basically like a three different functions that gets called, 4 different functions, the sequence after each other, and they all can return they all return a result, and all the values inside the error part of the result is a polymorphic variant. And the nice thing about this is, imagine if you wanted to try to do this with a normal variant. It would be really hard, because then we had to like define a type here, which is the invalid symlink. And then we need to define a new type here, which is basically the invalid symlink or the invalid config. And then we need to define a type here, which is basically this rresult message or the invalid config or the invalid symlink. But using polymorphic variants, we can just let the compiler solve this for us. So it looks something like this when we're actually calling this. Let's see, I have it here. No, it's not here. It's, where did I put it? Yes, here. So now we're actually running the program. And this is this config. This is a module that parses my config. It reads, and now I'm telling it to read from the /test folder, which is this folder. And then we have this like really convenient switch statement. So I told you before that when we're using the option type, like in the head function, our choice is like really binary. It can succeed or it fails. Then we get a none. But we implicitly know what the none means, because the only way the head function can err is if the list is empty. Here we still have this convenience of this like binary choice. We know it's either okay or it's not. The difference is that we can actually like pinpoint what kind of error happened. So within the error, we have different kinds of errors. Then we can report back to our user like, okay, so we got the invalid symlink. Okay, invalid symlink found, or the config is invalid. And then we can print the config, or we get the message, which is when we read it from the file system. They will say failed to read config file. So it's really convenient because the compiler can help us pinpoint the correct error and force us to handle all the errors. And we don't need to define the types. We can just shove in a polymorphic variant. And there's probably drawbacks to polymorphic variants compared to normal variants, but I haven't stumbled upon those yet. And I'll probably do in the future. But for now, for me, this has been really convenient, I said. Like when you're arriving here at the result switch statement, the code almost writes itself. And since the invalid symlink returns the invalid symlinks, we could do something nicer here to print all the invalid symlinks and then like compare them with the original and show some diff and like, yeah, these were the erring symlinks and those doesn't work, or here's the config is wrong. So, and just to end this, yeah, that's good. With Andreas saying you can mention some drawbacks. Someone needs to get me off my like high share. But for now, I think this is really nice, at least for me right now. I'm just going to run the program. Hopefully it works. Exactly. So we just made it. We found 3 valid symlinks, and this matches are here. And then we can try to remove everything. Yeah. Error. So this is basically the error we get from the S expression parsing. So this will be this part with the message. And then we can add that. So now we just have an atom. We don't have an actual list. Invalid config. And now we just print the config. So right here, run it. Yeah. So the config A is invalid. And this is not the most pretty error message. I haven't actually gotten to the part where I'll actually report this properly to the user, which is only myself right now. So. And we could also do something like this. So it matches the first case, which is this is in a list. But then we say like, oh, it's a list with a list, and we only have one thing here. And then, yeah, invalid symlink found. And since we haven't here in the invalid symlink, I haven't actually done anything pretty, but we should, with the help of the compiler, see what this is. Yeah, so this is a list of S expressions. And this would only be our invalid S expressions. So then it would be really easy to print this out and say like, hey, these are invalid S expressions. It doesn't match the source and the target S expression that we're expecting. And yeah, I think that's it. That's the thing I have to show you people, and the thing I wanted to show you. Do we have any questions, or otherwise that's it for me?
Excellent. Thank you very much.
Okay, thank you, people. Yeah, if you have, you can write down the questions or ask them later, because we have a little bit of break now, or.
Yeah, exactly. I think we'll have a 5-minute break before Andreas. I think we'll be good.
Yeah.
Thank you very much, Pontus. That was excellent.
Yeah, thanks for listening.